Okay, today we're going to finish off our medical physics topic with the last lesson. It's an extension to the ultrasound lesson that we began last time, and it's going to add something called the Doppler effect to our understanding of ultrasound. This is covered in the textbook at chapter 27.8, and it's very short. It's only 2 pages, and the first page is just a kind of introduction, and the second page is really just a worked example. This video itself is only going to be about 15 minutes long. Okay, so Doppler effect goes back quite a long way, 18th century, and it's an effect of any wave. It doesn't have to be ultrasound, it's light, sound, and it is an effect that occurs when there is relative motion between the source of the sound and the observer of the sound. So it's easiest to see it in practice, and I've got a couple of little applets that you can play with by downloading this PowerPoint yourself and following the links, but I'm just going to show one of them to you now. So if we just flick to this screen, what you've got here is the source S, which is emitting sound waves, which are traveling through space to an observer O. Each of these lines represents a crest of a wave. You can see that the a microphone attached to an oscilloscope at the source would record exactly the same as a microphone attached to an oscilloscope by the observer. Same frequency, same wavelength. What we're going to do, though, is not change the emission, but we're just going to move the source towards the observer. So as the source races towards the observer, what you see is that the source is chasing its own peaks of its waves, and it emits the next wave closer to the previous wave than otherwise it would do. What that means is that the observer O artificially sees the frequency of the wave increase. Even though the frequency of the sound wave that was emitted by the source didn't change, it is detected as a higher frequency. As the source rushes away from the observer, the opposite happens. The source is moving away from the last peak that it emitted, and so the subsequent peaks are further apart than they would expect it to be, and the frequency is lower than we thought it was going to be. It's not just an effect of a moving source, it's relative motion. So what we find as well is that if the source stays in one place and just emits the waves, if the observer moves towards the source, we'll get a similar effect taking place. So if we just take the observer and move it towards the source, you can see from the trace at the top of the screen that the frequency has again been detected as higher than it really is. And then if we take the observer away from the source, again, you see that the wavelength is longer and the frequency is lower than it really is. At no point does the frequency of the sound wave actually change. It is just the detected sound wave that is detected as either a higher or a lower frequency. This is known as the Doppler effect and is found throughout anywhere where there's waves. If you've ever heard an ambulance go past you and the pitch of the siren changes from a high pitch to a low pitch as it goes past, that's the Doppler effect. We also use it in cosmology to work out whether one star or one galaxy is approaching or receding from another star. Because it's got such a particular application in cosmology, the focus of your study of the Doppler shift is actually in the cosmology unit. However, I'm making reference to it here because it's important in terms of the application of ultrasound in medical scanning. Okay, so let's pop back to the PowerPoint and carry on. So it is, like ultrasound itself, a reliable and well-tested technology that has been around for 50, 60 years. It doesn't have a very high resolution, so it tends to only work if the blood is traveling quite fast. So we need to focus on the flow of red blood cells in arteries, and we're going to use the Doppler effect to try to work out how quickly the blood is traveling. So up until this point, we've been using ultrasound for static measurements. How far in distance terms is one organ or one tissue boundary inside the patient away from the probe? Now we're not too interested in distance because we tend to know where the artery is. What we're more interested in is how quickly are the red blood cells flowing in the artery. Okay, so if the blood cells are flowing away from the ultrasound, transducer, what you tend to find is that the frequency goes down. And that is because as the waves come in at their set frequency, one wave will bounce off a red blood cell, but when the second wave comes to bounce off the red blood cell has moved a little bit further away, and therefore the reflection is delayed ever so slightly, which means that the second echo is a little bit further away from the first echo. The wavelength has increased and the frequency has gone down. If, on the other hand, the red blood cells are coming towards the source of ultrasound, what you get instead is that the first reflection takes place from the red blood cell, and then before the second reflection takes place, the red blood cell moves up a little bit, which means that the reflection takes place a little earlier than was anticipated, which means that the frequency of the returning wave is slightly higher than the incoming wave. So whether the wavelength goes up or down tells us which direction the blood's moving in. But we can do better than that, because there is a formula that relates the change in frequency to the speed of the relative speed of the source and the observer. So delta F is the change in frequency, which is measured by the ultrasonic probe. F is the original frequency that is produced by the ultrasonic probe. C is the speed of the sound in the blood. And V is the consequent speed of the blood that is causing the shift in the frequency. There's a factor of 2 in this because we are dealing with a reflection. And when you deal with this formula, in fact, when you derive this formula in the cosmology unit, you'll find that there is no 2 in it for cosmology because there's no reflections. When we're just measuring light from a distant star, that light hasn't reflected off anything. It's just traveled from the source of the star direct. There's also this term theta. And you can see from this diagram that the change in frequency is caused by the relative motion between the blood and the source. So if the source is here, well, the observer is here, the source of the blood, which will be the source of the reflections, if it's moving parallel to the direction the detector is pointing in, then there will be maximum change, maximum shift, given that the blood cell will move the most in this direction to reduce the wavelength between successive reflections. However, if we were to move the probe up here to the 90-degree position, then we would find that there would be no effect because the blood would be moving perpendicular to the direction of the waves, and therefore there would be no shortening or lengthening of the wavelength in between reflections. And you can see from the formula that if we set theta to be 90 degrees, cos of 90 is 0, and we would get 0 change in frequency. This formula will be given to you on the datasheet. I just need you to make sure that you are comfortable using it. Okay, so here is an example. I suggest that you pause the video at this point and try not to peek too much at the answer. Record these numbers and put them into the formula and see if you can work out what speed the blood is flowing at. Okay, so you can pause the video and do that, but I'm going to move on. This is a photograph of the probe pointing at the skin, and you can see that the angle here is around about 60 degrees, and that's about normal. If you come much below 40 degrees or so, you find that the ultrasound tends to bounce out of the skin rather than travel through the skin to the blood to provide the measurement. The trace that is produced is called an echocardiogram. Don't muddle that up with another ECG called an electrocardiogram, which is probably what you're more familiar with if you've ever seen anything like this on a medical drama on television. The traces look the same, but it's different technologies and different origins, although they do measure similar things. In this particular case, we're measuring blood flow, and you might remember that the heart beats kind of twice. It sends the blood around the body with a high pressure, and then it sends the blood to the lungs at a lower pressure. So you can see the multiple beating of the hearts that's taking place here. And you can see in particular that these traces are quite uniform. The spacing between beats is uniform, and the peaks of intensity in these traces is uniform. So this uniformity represents a healthy trace from a healthy patient. The line represents a zero frequency shift. So above the line, we have blood traveling in one direction, and below the line, we have blood momentarily traveling backwards in the other direction between beats. Okay. Common uses of an echocardiogram are not examinable, but some of you will be thinking of going on beyond your physics towards a medical application. And so just listed on the screen are some medical applications that you can use an echocardiogram for, but you wouldn't be expected to reproduce any of these things on an exam paper. The bottom line is that we use it for checking if blood flow is as it should be. And that can be blood flow due to the beating of the heart, as the examples on the screen are indicating, or it can be blood flow due to the arteries. So if we just have a little look at an example of an artery. So here's the echocardiogram that we've just been considering. Here's a two-dimensional graphic of it instead. And the representation here is that reds and yellows and oranges are blood traveling in one direction, and the blues are blood traveling in the other direction. So this darker area here, this is the inside of the artery, and you can see that this section of blood that's been picked up on the trace is all traveling in the same direction because it's all reds. And actually, the colors are fairly uniform, and so most of this blood is all traveling at the same speed. So this is a nice, smooth flow of blood through the artery. What we can see on this trace, however, is the chaos that's in the echocardiogram, but in the two-dimensional representation above, you can see some blues now. And this blood is actually swirling here. Some of it's traveling backwards. And that's because the artery has been narrowed, most likely because of fatty deposits against the artery wall. And this has made the artery walls less smooth and is creating a little bit of turbulence in the blood. And this won't be healthy for the patient. It can cause high blood pressure. And you also don't want these fatty deposits to break free and cause problems elsewhere in the body, or to even clog and narrow so much that the blood can't flow through this artery. So again, you don't need to interpret any medical imagery for what these traces mean. You just need to be aware of the fact that the Doppler effect in conjunction with ultrasound produces a medical imaging technique called an echocardiogram that can be used to judge whether the heart is beating regularly, whether the valves in the heart are functioning properly, and whether the blood is traveling through normal arteries or narrowed arteries. Okay, that actually concludes this lesson and also the medical physics topic. I've got a little bit, and it really is a little bit, of follow-up work from today's lesson. As I said to you earlier, it's only 2 pages in the textbook. One of those pages is really an introduction, and the other is just that example I just showed you. So there's very little to this. All I really need you to note are words like Doppler effect, echocardiogram. And if you could copy the formula out from the textbook and maybe make a note to yourself that in the cosmology topic, you will revisit it and you will see where it comes from. If you could then have a little look at the 4 questions that are at the end of the 27.8 chapter and do those, and then that will conclude your medical physics. What I will ask you to do later in the week as well is, later in the week, is to complete the end of chapter questions as well, which have some more questions that are more of an exam style level rather than the scaffolding questions from the end of the chapter. Okay, good luck with that, and well done for finishing the topic.